Dress science video. Yay! Yeah, I've been really busy. No time to even take notes for what I'm going to say. But I'm going to do this electromagnetic spectrum crap, physics and such, and talk about it a little bit. And in kind of vague, open terms, sort of, kind of. But anyway, kind of looking for a conversation or input by somebody else or with somebody else or whatever. Just if you have some sort of, oh, that can't possibly be the truth kind of stuff or whatever. Input, snarky crap I can live without. But, yeah, got something to add. I can always footnote you. Anyway. Alright, so you got this let's just get on with it, right? Alright, so you got this electromagnetic spectrum thing. So here's all the energy, is sort of in here somewhere. So you start with radio waves, microwave, infrared, visible light, ultraviolet, X-rays, gamma rays. Alright, so the thing that's tricky is here in this visible light thing. We know that light can be filtered, so that sort of indicates to me that it sort of has a shape. Because if we have let me do this drawing, see how this drawing thing works. It's pen, I need a brush. Alright, so polarized film basically works by having bars like this. Alright, and what happens is some light gets through and some light doesn't get through. And the only reason why some light couldn't get through is because I think it's, short, well, here, let me get another color for the... I think it's sort of shaped like, I guess I should have hit the other button. It's alright, I just put a little red on top of the black. There we go. Yeah, that's cool. Anyway, I'm thinking it's like shaped. Okay, and so when it's shaped, when it's flat this way, let's say it's a triangle, it can't get through the bars. It hits the bars. So it has to get refracted in some way. But if it's on a straight edge, more of a straight edge, so it's thinner, well, that's not a very good drawing there. But anyway, you get the idea, right? Sure you do. If this is turned, rotated, like this way, it's straighter, and so when it's straight, it can go through the bars. And so then the second layer of film would have the bars go the opposite direction, and theoretically, that would block out all the light. Because if the light is this straight way to get through here, it's going to hit those bars, and vice versa. So that's sort of my understanding of polarized film and how it filters the light. So light has a shape, is what I'm basically saying, and that sort of makes you think. If light is shaped, then maybe we can figure out, what the shape is, and maybe the shape has something to do with all of this stuff over here, like how this is different than that. So my theory is, I've talked about a clock speed for the universe, but yeah, there's this idea of distance, right? And distance is just saying you get from point A to point B. So we call that A, and we call this B. And this is just a matter of time. So at the speed of light, there's a certain amount of distance you can travel in one quantum, let's say, of time. So this quantum thing, I like this word quantum, but people keep using it for different things. So let's just say that the quantum is either a unit of time, which would be a clock tick. Every clock tick, everything in the universe does something, and then it stops, and then it does something. On every clock tick, it jumps from A to B. And that's what we perceive as a portion of the speed of light. Or conversely, you can just say that it takes this amount of time for this thing to move from A to B at the speed of light. At the speed of light, you get from A to B in this quantum of time. So it's either a quantum of distance or a quantum of time. It doesn't really matter. You're going the same distance at the speed of light. That's the fastest anything can move, is the speed of light. And so everything else is just... everything else on this spectrum is moving at the speed of light, and the only thing that slows it down is that it sort of bounces off of stuff. So it comes in here and it bounces off that, and it bounces off that, and it bounces off that. So if it's going through matter, like the universe, I mean like the atmosphere, see here's the indications of what gets through the atmosphere and what gets blocked. And the blocked we don't know, it doesn't say here whether it gets absorbed by the atmosphere or whether it's actually reflected by the atmosphere. And that brings up a whole bunch of more questions, because then you got to wonder, you know, when they say blocked or absorbed, what is that exact? Woo, that's not exactly a good color. I'll have to change my color to some other color. Anyway, so let's say where was I? Yeah, absorbed or reflected. So usually when we think of reflection, you know, whoops, I don't want to square, but we'll use it for now. We think of something comes at something like a little round ball here, okay, and it comes at something like this, and it bounces off, and it goes this way, and then it's going over here. Now what's really happening though is it's an energy transfer. The thing hits here, comes in and hits, but it pushes, and then it's going in a new direction. A new side of this thing is now moving in this new direction. So it's like the particles are substantially moving in one direction, and then the quantum are somehow moving in this other direction. But there is this transfer of which parts are moving in which direction. I'm not saying that exactly the way I want to. But the point is, if the cue ball is looking at you, coming at you with like a face rolling on one side of the cue ball, when it bounces away, it's going to have a different face showing. It'll be rotating on a different axis, is my point. So there's a transfer of energy. And then when something's absorbed, something can also be absorbed and it can shoot out bits of itself. So instead of the ball coming out, little particles of it can be released. So in a sense it's a reflection, but what's getting reflected is bits, because it breaks into pieces, or it goes inside of the material itself. It hits some atoms inside of it, and those atoms release photons or some other energy. But there's a transfer and an equality in terms of what went in ends up going out. So an equal but opposite reaction kind of effect. Well, anyway, I don't want to get into a whole, but see, that's the trick here, is that, you know, if we say that the things are made up of little atoms spaced about, depending on their temperature, and so when something comes shooting in, you know, if it hits an atom, well, then it's going to get absorbed, in the sense that its energy, it's going to be an energy transfer, or an energy transformation. And little bits of this thing that break off might fly into another atom, and then it might actually release the end result energy that comes. So there could be a transfer through this process, and that's what also slow down something, so it wouldn't be traveling at the speed of light anymore, because of these reflections, this bouncing around that can take place as it's getting modified. It's sort of how electricity, I think, travels. But anyway, we won't get into that. I don't want to really talk about electricity yet. So anyway, the idea here is that this whole thing is all made out of just quanta, you know, just stuff. All this is just single stuff. And so at this end, let's just say there's one thing, a gamma ray, let's say. So gamma rays are the smallest thing in the universe, let's say. So let's just make a little gamma ray here. Well, yeah, I gotta learn how to draw. It's been a long time since I used this program. All right, so that's the smallest thing, is the gamma ray. It's just a single little piece of quanta. So that's all it is. It's just a quanta. So we'll just call that one quanta, 1Q. Ooh, that doesn't look right. So that's what that is. And then we could say a radio wave, or the electrons that make up a radio wave, we call them electrons, but it might be more complicated than that. Or anything, as we move down this scale, as we move down to this more intense scale, more intense in the sense that it's bigger, and this is smaller. So this has a higher frequency, you know, because they're closer together, because they're smaller, and this one has the bigger frequency because there's more of them and we don't recognize the frequency because we are seeing them as a chain rather than a singular item. So anyway, so you have one quanta at this end. So a gamma ray, let's just say, is a 1. And then at the other end would be a long radio wave, which would contain maybe billions of quanta. So one radio wave would be a billion of these little things stuck together in some manner where they're tied to each other. Now that's the manner part is the part I'm getting to. So it could be a billion, and you know, I'm not going to write out billion. It's a billion Q's there for a radio wave. And we call that, maybe we call that an electron. Maybe one electron is made up of a billion gamma rays. So there's a billion gamma rays in one electron, maybe. That could be the truth of the thing. And electrons might not all be of the same energy, which might be a whole nother subject. But anyway, let's not get into that, because the point I wanted to get to was the shape thing again. I want to get back to this idea of a shape. And so if all of the things on this thing did have a shape, like say a 1 quantum was shaped like a diamond, okay, and that's all it was. Well, if you added other quantums to it, they could, if they come in the right number, form an identical shape. So they could end up with the same shape, now larger. Alright, so now it's, instead of just 1 quanta, it's got 4 quanta, but it's the same shape. It can do the same twisting and turning. So we could say that these different levels of electromagnetic spectrum just indicates how many quanta the thing is made out of. And so again, a radio wave could be huge in terms of the number of quanta it's made out of, and they're just added on just the way, well, that was ugly. That wasn't done very well, but it would be a multiple of, you know, 2, 4, 6, you know, would be the add-on. So you start off with 1, then 4, then 6, you add 6, and then you add 8, and then, you know, just keeps going like that to maintain the same shape. And so, yeah, I haven't done the math yet, but something like that anyway. And what also could take place over time is that these packets could work as units. So little 4 packs could add on to something, and so it could have less of the distance from here to here could be less, and it could end up just lengthening. So there's two things that would be that would define the item, the thing. It would be its length and its width. And so we could sort of look at the length here as we got frequency, and we got width. It would be the amplitude. So that kind of fits with that kind of theory, or that kind of, it kind of fits the obvious imagery of this length for amplitude and frequency. But now there's also a trick where they could theoretically also have a shape that could be very, they could have the shape, the required shape that they're always in, but they could also be hollow. And so that could be a low intensity, a low collective energy, because it's hollow, but it's still made up of a bunch of quanta, but maybe only 1,000,000 instead of 1,000,000,000 that it would be made up of if it wasn't hollow. And that might have to do with the strength of things like radio waves and their survivability. But that's a whole nother gnarly mess. Yeah, but this might be how they're tied together, and there might be some flexibility as they get bigger and bigger in terms of stretching, so they can get wider or they can get longer. But they're still very small. They could be still the size of as we would detect them as an electron, but that's how we perceive them. It's not how they actually might be. So there are, like a school of quanta would be an electron, and they're all moving in exactly the same way, the same direction. each one. And so movement's the other part of this thing that I wanted to get to, if I haven't completely confused you. So the standard model of atoms, whoops, yeah, that wasn't too cool. The standard model of atoms, I don't know why that, anyway, standard model of atoms, you know, you got the nucleus, yeah, draw. Okay, you got the nucleus thingy, and then you got the little orbiting electron. You know, and they have different orbits. Yeah, that's really bad. But anyway, you get the idea. And the thing would be is that my argument would be is that all matter is made up of quanta moving at the speed of light. So there's nothing else in the universe. That's what everything is made up of. And so the nucleus, the neutrons, and the protons are made up of quanta moving at the speed of light that are just trapped in a circular orbit around that tight nucleus. And we just don't know how to, we can't perceive it because it's so small that we don't realize that that's what it's doing. But if they're just moving just like these electrons in the outer shell, they're just moving the same way on the inner shell. It's just trapped energy. And when that energy is released, when the gravitational pull, what might be called the strong and weak forces, are allowed to freeze something because something happens to that force that holds it in this orbit, it just shoots off. You know, shoots off like a photon of light would just shoot out of an atom. All it means is that a piece of an electron, you know, one of those quanta, that the billion quantas that this electron is made out of, one of the pieces shoots off, a piece big enough to be called visible light or ultraviolet or an X-ray. So it's a section, a piece of the school that was the electron just is liberated. It's no longer gravitationally held, so it just flies free again at the speed of light. Now the thing is, at any one time, the orbit could be going in any one direction, right? I mean, it's lots of directions depending on when you catch it in time. You know, at one point in time it's here, another point in time it's here, another point in time it's here, it's here. It's always in a different point of time moving at the speed of light. So I conjecture that the reason why matter can't be accelerated, matter would be an atom, would be anything that has energy trapped in an orbit is called matter. That can't be accelerated at the speed of light because the directionality of the quanta is always wrong. Some portion of the quanta might be moving in the right direction, but some other portion of the quanta is moving in the opposite direction, or in some other sideways direction. And the only way the matter can be accelerated is all the quanta have to be liberated in the same direction. So they have to be released at the same point in the orbit. So every time one goes around, another piece gets released in the right orbit. Another piece gets released in the right orbit at the right moment in the direction that is intended to travel. So theoretically, if it released all of its energy at just the right time, in just the right direction, let's say, all the matter in all the energy in the atom could be released at the speed of light in one direction. But it would be, obviously some would be further ahead of others would be behind, but as a stream of energy it would seem as if it was all moving in that direction. But anyway, that's one way that all the energy could be, all the energy inside of an atom could be migrated to the speed of light, is just releasing all the quanta at just the right point, so they're all released in the direction of the desired movement, or whatever you want to call it. So anyway, if you reduce this all to a clock speed, then all this relativity stuff, like the fact that you have a train, well, let's just say a car, it's a box with wheels. So you have a box with wheels moving this way. You know, that the point is that the light bouncing off of this box can't be moving faster than the speed of light. So even though the box is going 50 miles an hour, this light isn't moving 50 miles an hour plus the speed of the box. That doesn't happen. And the reason why it doesn't happen is because on the quantum level, everything's still moving just that one piece of distance. It can't move any more than that. And what's dictating that is easily understood if you just reduce it to a clock speed. So only on the clock speed, only on the click, does the light move. So the car isn't really moving when the photons fly. And so for them there is no velocity, there is no momentum. There's only moving one quantum of distance in a direction, and that's all they can do, and that's all they ever do. And there's no gaining velocity or increasing velocity or decreasing velocity. There's only moving from one space to another, period. So on their level, the relativity fits and makes sense, and also explains why the speed of light is a constant, and it can't be you can't accelerate anything faster than that. Yeah, so that's probably enough of a video, because it's going to be terribly confusing. But anyway, I've got to write all this stuff up. I think there was something else I wanted to get to, but the important thing is these concepts: the idea of a clock speed, the idea of energy having a shape, okay, like light, where it can be filtered because of the fact that it has a shape, and that it all has that shape, and that the difference between this and this is merely the fact that this is few quanta and this is many quanta. And that's about it. Yeah. As individuals, you could have gamma ray radiation that would be very intense, that would be just as intense as a radio wave, but it would just be a whole bunch of single particles, where this is a school. So you could have a huge number of single gamma rays, but they wouldn't be a school. They wouldn't be connected to each other, and that's just the difference. This is a stream of connected quanta, and these are a stream of unconnected quanta. But as discrete individual things, obviously there's a huge difference. Okay, so sort of, well, anyway, it gets complicated. Anyway, gotta write a book, a paper, whatever, gotta do something with it. But eventually, I gotta think a little bit further. Like I said, there's a couple more things I want to throw in here that I realized, and I'm just not remembering them. But I'll come back to it. This is a good subject. So anyway, thoughts appreciated. Until next time.